Lots to dig into.
And our mission today, well, it's a deep dive into something really fundamental. It's about how electrons arrange themselves in atoms,
Hmm.
specifically how their energy levels are, well, restricted.
That's really the heart of it, isn't it? The sources hammer this home. Electron energy isn't just anything goes, it's quantized,
Quantized, meaning,
meaning electrons are stuck with specific, discrete amounts of energy. They can only exist at certain levels. It's a fundamental rule, and it dictates where you'll find them.
and finding them brings us to orbitals. The sources talk a lot about these. It's not the old picture, right? Like tiny planets.
Not at all. Forget the simple orbits. These orbitals, according to the sources, they're mathematical functions. They tell you the probability, the likelihood of finding an electron in a certain region.
So less of a path, more of a probability cloud.
Exactly. A shift from certainty to probability. So that's our goal today. Unpack this link between quantized energy and these electron orbitals.
We'll look at how the idea developed, the
Right.
history,
Yeah.
the specific rules, these sort of quantum numbers they mentioned,
Right, the address system.
and crucially, the proof, the actual evidence we can see.
Let's do it.
All right, so diving in, the sources really emphasize this first point. Electrons have to be in these discrete energy levels. No in-between allowed.
Yeah, and what's maybe a bit weird coming from our everyday world is that this isn't just some external rule forced on them. It actually comes from the electron's nature.
How so?
The sources explain it stems from quantum mechanics. Specifically, the electron behaving like a wave when it's trapped inside an atom. That confinement, its wave nature, it naturally leads to quantization.
Okay, so how did we even get to this idea? I mean, where did specific energy levels first pop up?
Well, the sources point back to Niels Bohr around 1913. He was trying to solve a big puzzle.
Which was?
Why do atoms, when you heat them up or zap them with energy, only give off very specific colors of light?
Yeah.
Distinct lines.
The line spectra, like a unique barcode for each element.
Exactly like a barcode. So Bohr proposed this model. Electrons orbit the nucleus, yes, but only in certain specific paths. Allowed orbits, he called them.
And each allowed orbit had its own energy level.
A distinct, fixed energy level. And crucially, he said they could stay in these orbits without losing energy, which classical physics couldn't explain.
But they could jump between them.
Yes, the famous quantum leap. An electron absorbs a specific chunk, a quantum of energy, maybe from light, a photon, and jumps to a higher allowed orbit. Then, to fall back down, it spits out a quantum of energy, again, often as a photon.
And the energy of that photon had to match the difference between the orbit levels exactly.
Precisely, which explained those specific spectral lines. It was revolutionary.
But as the sources mentioned, it wasn't the whole story.
No, it was incomplete. It worked well for hydrogen, but struggled with more complex atoms, and it didn't really explain why only those orbits were allowed.
So enter quantum mechanics.
Right. And specifically, Erwin Schrödinger in 1926. His wave equation gave us a much deeper understanding.
He treated electrons as waves, not just particles.
Exactly. And here's the kicker, the direct link back to quantization we started with. The sources explain that when you solve Schrödinger's equation for an electron confined in an atom, the math itself, it only gives you sensible, valid answers for specific, discrete energy values.
Wow. So the quantization isn't just assumed, it falls right out of the mathematics.
It's baked into the cake. That mathematical requirement is the origin of quantized energy levels. It's a direct result of the electron's wave nature and being trapped in the atom.
Okay. And the solutions to the equation, those are the wave functions, psi.
That's right. The wave function describes the wave state. But if you square it, that gives you the probability density.
Where you're likely to find the electron.
And those regions of high probability, that's what we call orbitals now, these probabilistic clouds. Very different from Bohr's neat little paths.
So these orbitals, coming from the math, they have specific properties, energy, shape, orientation.
And that's where the quantum numbers come in. The sources lay out 4 of them. Think of them like an address. They define the state of an electron.
Okay, let's break them down. First one.
First is the principal quantum number, n. This is the big one. It tells you the overall energy level and, roughly, how far the electron is from the nucleus. It's just positive integers. 1, 2, 3.
Higher n, higher energy, further out.
Basically, yes. Orbitals with the same n form an electron shell.
Okay, like the main floor of a building. What's next?
The azimuthal quantum number, L. This determines the shape of the orbital, and it defines sublevels within a shell n.
Okay,
Yeah. L can be an integer from 0 up to n1. The sources say L0 gives you a spherical s orbital. L1 gives dumbbell-shaped p orbitals, L2, more complex d orbitals.
So L is like the style of the room on that floor.
Good analogy. It relates to the electron's angular momentum.
Got it. Then there's a magnetic quantum number, NL.
Right. This one describes the orbital's orientation in space. For a given shape L, ML can be any integer from LL through 0 up to plus L.
So for those orbitals where L1...
Exactly. ML can be MeV 1, 0 plus 1. That corresponds to 3p orbitals, same shape, same energy sublevel, but pointing along the x, y, and z axes.
Okay. Floor, N, room style, L, and which way it's facing, ML, makes sense. And the last one.
The spin quantum number, EMS. This isn't really about the orbital itself. It's an intrinsic property of the electron. Think of it like, well, it has its own tiny magnetic moment. It can only have two values, plus 12 or negative 12, often called spin up and spin down.
And this is where that other rule the sources mentioned comes in. Pauli.
The Pauli exclusion principle. Yes,
Gosh.
crucial. It states that no two electrons in the same atom can have the exact same set of all four quantum numbers, N, L, ML, and Ms. It means each specific orbital defined by N, L, and ML can hold a maximum of 2 electrons, and if it holds 2, they must have opposite spins, 1 plus 12, 1 against 12.
Ah, okay. That explains how electrons fill up these energy levels in shells.
It dictates the entire structure.
Right. So we have this elegant quantum mechanical picture. Specific energies, specific orbital shapes and orientations governed by these numbers. But how do we know this isn't just clever math? Where's the hard evidence?
And we circle right back to where Bohr started, those atomic spectra. The sources really emphasize this. It's the key observable proof.
Because the energy levels in this model are the energies of these specific orbitals.
Precisely. So when an electron jumps, say, absorbs energy, it jumps from its current orbital to an empty, higher energy orbital. And the energy absorbed has to exactly match the difference between those two orbital energies.
And when it falls back down?
It emits a photon with energy exactly equal to that energy difference between the higher and lower orbital.
And since only certain orbitals with certain energies exist...
And only certain energy differences are possible.
Meaning only photons of specific energies, specific wavelengths, specific colors can be emitted.
You got it. That's why we see those sharp lines in the spectrum. Not a continuous rainbow. Each element's unique line spectrum, its light fingerprint. The sources are clear. This is direct, observable proof that electron energy is quantized. It's a direct result of electrons being confined waves occupying these specific orbitals.
Wow. Okay, so pulling it all together from what we've read, the orbitals aren't just locations. They're the reason energy is quantized.
That's the core message in the sources, yes. The electron's wave nature, when confined, mathematically demands discrete energy states, and each state corresponds to a particular orbital cloud.
And understanding this, it's not just abstract physics, is it?
Absolutely not. This underpins everything. Atomic structure, how atoms bond to make molecules, that's all of chemistry right there.
Yeah.
And how matter interacts with light, lasers, LEDs, spectroscopy. It all comes back to these quantized energy levels and orbitals. It seems abstract, but it shapes a physical world you interact with constantly.
It really does.
And think about that evidence again, those incredibly precise spectral lines, unique for every element. It tells you these energy jumps between orbitals aren't just theoretical ideas. They are real, exact, measurable things happening.
That precision is amazing. It's like nature has this incredibly fine-tuned rule book.
So maybe it's something for you to consider. Given that electrons really can only be in these specific states, these orbitals with these exact energies, and we see the proof in the precise light they emit when they move, what does that fundamental order tell us? Does it make the universe feel more predictable at its core, or perhaps more strangely specific?
Or even just thinking about technologies, like lasers, they depend entirely on getting electrons to make one very specific jump, emitting one very specific color of light.
Exactly. It's harnessing that fundamental quantum rule.
It really is fascinating. Diving into these sources definitely reveals this hidden layer of, well, elegant rules governing reality, makes you think.